Our universe is hiding secrets that break every rule we think we know. We are about to explore 30 cosmic phenomena that challenge the very boundaries of modern physics. This is a journey into the most perplexing mysteries of the cosmos, where established scientific principles are pushed to their absolute limits. Understanding these puzzles is not just for astrophysicists. It is for anyone who has ever looked up at the night sky and wondered about the fundamental nature of reality. We will uncover cosmic riddles, from the force of dark energy accelerating the universe to the spooky connection of quantum entanglement in the void of space. Each one defies conventional explanation and forces us to rethink everything. By the end of this, you will see the universe not as a settled picture, but as a living frontier of unsolved wonders. We will ask why the cosmos is expanding faster than it should, and what invisible scaffolding holds galaxies together. What do you think is the most profound mystery waiting for us in the dark? Everything we thought we knew about cosmic destiny was wrong. For decades, the prevailing wisdom held that the universe, born in a fiery explosion, would eventually slow its expansion. The mutual gravitational pull of all matter, the great cosmic glue, was expected to be applying a constant brake. Then, at the turn of the millennium, two independent teams of astronomers made a shocking discovery. By observing distant stellar explosions known as Type I, a supernova, they found that the universe is not slowing down at all. It is speeding up. Something is actively forcing space itself to stretch apart at an ever-increasing rate. This something is what we call dark energy. It is an invisible, repulsive force that permeates the very fabric of the cosmos. Think of it as the ultimate anti-gravity, a constant pressure inherent to empty space that pushes galaxies away from each other. The most staggering part is its dominance. Dark energy is not a minor player. It constitutes about 68% of the entire mass energy content of the universe. This means the force driving the cosmic expansion is the primary component of reality, and we have no idea what it is. Cosmologist Michael Turner called it the most profound mystery in all of science. One of the leading candidates for dark energy comes from Einstein's own equations, a term he called the cosmological constant. He initially introduced it as a fudge factor to keep the universe static, later calling it his greatest blunder. Now it might be his greatest accidental prediction. Yet when physicists try to calculate its expected strength using quantum mechanics, the result is wrong by a factor of 1 followed by 120 zeros. It is the worst theoretical prediction in the history of science. The evidence for dark energy's reality is now overwhelming, etched into the afterglow of the Big Bang, the cosmic microwave background, and confirmed by the large-scale structure of the universe. But its nature remains utterly elusive, so we are left with a haunting question for the future. If this mysterious repulsive force continues to dominate, what ultimate fate awaits the cosmos? A cold, dark, and eternally expanding emptiness where galaxies are ripped beyond the cosmic horizon. This force that sculpts the universe on the grandest scale finds a strange and unsettling parallel in the behavior of the universe on the smallest scale, a phenomenon that connects particles across unimaginable distances. While dark energy pushes the cosmos apart on the grandest scale, another invisible force holds it together. Every galaxy spins like a colossal pinwheel of stars, yet they are spinning far too fast. According to the known laws of gravity, these galaxies should tear themselves apart, flinging their outer stars into the void. They do not. Something unseen provides the extra gravitational glue, a hidden scaffold that keeps them intact. This is the enigma of dark matter. It is a substance that does not emit, absorb, or reflect any light, making it completely invisible to our telescopes. We only know it is there because of its powerful gravitational pull on the things we can see. It binds galaxies and shapes the entire cosmic web. In fact, dark matter makes up about 27% of the universe, outweighing all the stars, planets, and nebulae combined by a factor of more than 5 to 1. The evidence for this cosmic phantom emerged from the meticulous work of astronomer Vera Rubin. She measured the rotation speeds of stars in distant galaxies and found something astonishing. Stars at the outer edges were moving just as fast as those near the center. This defied all expectations. It was as if the entire galaxy was embedded within a giant, massive halo of something we could not see. Her findings provided some of the strongest proof that the universe is dominated by matter we cannot detect. Another line of evidence comes from gravity's ability to bend light itself. When we look at a distant galaxy cluster, its immense gravity can act like a lens, warping and magnifying the light from objects even farther away. This effect, called gravitational lensing, allows us to map the cluster's total mass. Time and again, these maps reveal that most of the mass is not where the visible galaxies are. It is spread out in a vast, invisible cloud. This was spectacularly demonstrated by the Bullet Cluster, a cosmic collision of two galaxy clusters. In that event, the hot gas of normal matter, which we can see with X-ray telescopes, slammed into itself and slowed down, but the dark matter, which does not interact with itself or normal matter, sailed right through. The result was a clear separation. The mass mapped by gravitational lensing was in a different place than the visible matter. We were literally seeing the shadow of dark matter. So what is it made of? Physicists have proposed exotic particles that barely interact with normal matter. Leading candidates include WIMP, or weakly interacting massive particles, and actions, which are theoretical ultra-light particles. Decades of sensitive experiments deep underground have tried to catch a fleeting glimpse of these particles, but so far, every detector has come up empty. Dark matter stands as a fundamental challenge to the standard model of particle physics, our most complete theory of the subatomic world. The model simply does not account for this immense, invisible component of reality. Its existence forces us to invent entirely new physics. So as you look at the night sky, consider this. The stars and galaxies you see are just the visible decoration on a hidden framework. Most of the universe is made of something we cannot sense, a ghostly presence that governs the motion of everything. This invisible architecture not only holds galaxies together, it also creates the cosmic structures where even stranger things can happen, leading us to the violent hearts of galaxies where spacetime itself is torn apart. But this cosmic scaffolding of dark matter is not the only puzzle written into the ancient light of the universe. When we peer back to the very edge of time itself, we find a different kind of mystery, one of impossible uniformity. The afterglow of the Big Bang, the cosmic microwave background radiation, paints a nearly perfect picture of sameness across the entire sky. No matter which direction you look, the temperature of this primordial radiation is identical to 1 part in 100,000. This presents a profound logical problem. In the standard Big Bang model, there simply has not been enough time since the beginning for light or heat to travel from one side of the observable universe to the other. These distant regions have never been in contact, never had a chance to exchange information and balance their temperature. It is as if you walked into a vast room where 1 million people who have never met or spoken are all humming the exact same note in perfect pitch. How could such perfect thermal equilibrium be achieved? Cosmologists call this the horizon problem. and it fundamentally challenges the standard story of the universe's birth. To resolve this paradox, physicist Alan Guth proposed a radical new idea, the theory of cosmic inflation. He suggested that in the first fleeting fraction of a second after the Big Bang, the universe underwent a period of hyper-accelerated, exponential expansion. During this incredible growth spurt, a patch of space smaller than a subatomic particle was stretched to a size larger than our entire observable universe in less than a billionth of a billionth of a billionth of a second. This violent, sudden stretching would have ironed out any primordial wrinkles, smoothing the cosmos to the incredible uniformity we observe today. It would have taken a tiny, connected region and blown it up to become our entire cosmic horizon, explaining why everything looks the same. This theory also makes a key prediction that such a process would have left the overall geometry of the universe flat, not curved like the surface of a sphere or a saddle. And remarkably, our most precise measurements from satellites like Planck confirm this. The universe is flat to within a margin of error of just 0.4%. The data overwhelmingly supports the inflationary model, yet it is not a complete picture. The Planck data also revealed subtle, unexpected anomalies, strange asymmetries, and cold spots that the simplest models of inflation cannot easily explain. This leaves us with a haunting question: was inflation a single, violent event, or could it be part of a deeper, more cyclical process in a multiverse? What fundamental mechanism could have triggered and then stopped this super expansion, and what exotic physics governed that first moment? This search for the engine of inflation pulls us even further back in time, to an era dominated by particles and forces beyond our current understanding. The same cosmic expansion that smoothed the universe may have swept its attic clean of another profound mystery: grand unified theories which attempt to merge the electromagnetic, weak and strong nuclear forces, make a bold prediction. Our universe should be flooded with relics from its earliest, most energetic moments, particles known as magnetic monopoles. These are not like the magnets on your refrigerator, which always have both a north and a south pole. A magnetic monopole would be a fundamental particle that is just a north pole, or just a south pole, existing completely on its own. Finding one would be as revolutionary as discovering an electron without its positive counterpart, the proton. The legendary physicist Paul Dirac first showed that the existence of such a particle would perfectly explain a profound fact of nature: why electric charge comes only in discrete, quantized units. If monopoles exist, then charge quantization is no longer a mystery, it is a mathematical necessity. Yet, despite decades of searching, not a single, definitive magnetic monopole has ever been found. This glaring absence is a major crisis for particle physics. If our theories about the universe's unification are correct, these particles should be everywhere, so common that they would be impossible to miss. Their total absence suggests that our theories are fundamentally flawed, or that something extraordinary happened to hide them from view. This is where cosmic inflation provides an elegant, though speculative, solution. Think of the early universe as a container filled with an incredibly dense soup of magnetic monopoles. Then, inflation happened. That sudden, violent stretching of space-time would have diluted this primordial soup to an incredible degree. The once crowded monopoles were spread so far apart that, in our entire observable universe, we might be left with only one or two, or perhaps none at all. The vacuum cleaner of inflation could have made them virtually undetectable. This clever fix links the monopole problem directly to the horizon problem, suggesting one grand event resolved two major cosmological puzzles at once. The hunt, however, is far from over. Experiments like Mo-Edel at the Large Hadron Collider are actively searching for the telltale signatures of these elusive particles. They use stacks of special plastic films like a physicist's flypaper, hoping to catch the unique, heavy damage trail that a monopole would leave as it passes through. To understand why finding one would be so transformative, consider electricity. We can have a positively charged proton sitting alone or a negatively charged electron by itself. Magnetism, however, seems to be fundamentally different, always appearing as a paired dipole. The discovery of a magnetic monopole would finally symmetrize this picture, showing that electricity and magnetism are even more deeply connected than we thought. It would rewrite our textbooks on electromagnetism, so we are left to ponder a deep question. Why does nature seem to avoid these isolated magnetic charges that our most elegant physics demands? Is it because they were wiped away by inflation, or is the universe trying to tell us something even stranger about the fabric of reality? This search for a missing particle is a quest to find a fundamental piece of the cosmic puzzle, a quest that continues with another ghost, one that seems to travel faster than light itself. That search for a missing magnetic charge, a relic of unification, points back to the very mechanism that might have erased it, a process of unimaginable speed. In the first sliver of a second, a fraction so tiny it defies human comprehension, the universe did not just expand, it exploded in scale. This is cosmic inflation, a theory proposing that our entire cosmos underwent a hyper-accelerated growth spurt, doubling in size over and over again, far faster than the speed of light. This was not a violation of relativity because it was space itself that was stretching, carrying energy and matter along for the ride. The engine for this phenomenal event is thought to be a hypothetical field, the inflaton field. Picture this field as a kind of cosmic landscape. In its earliest state, it was perched high on an energy hill, filled with a strange, repulsive gravity that pushed space apart with incredible force. As this inflaton field slowly rolled down its energy slope, it released that pent-up energy, transforming it into the hot soup of particles and radiation that would become our universe. Physicist Andrei Linde expanded this idea with his concept of chaotic inflation, suggesting that this process might not be a one-time event. Instead, tiny patches of space could randomly trigger their own inflationary periods, giving birth to entire universes in an endless, bubbling multiverse. This single idea of inflation elegantly solves two of our greatest cosmological puzzles. It explains the horizon problem by taking a tiny, connected region and stretching it into our vast, uniform cosmos. It also accounts for the flatness problem because inflating a curved surface to an immense size makes it appear perfectly flat, just as the surface of our planet seems flat from where we stand. But inflation did more than just smooth and flatten. It also planted the seeds for all future structure. The quantum fluctuations that are an inherent part of any field were present in the inflaton field. As space inflated at a breathtaking rate, these microscopic jitters were stretched to cosmic proportions. They became tiny variations in density, the gravitational seeds around which dark matter and normal matter would eventually clump, forming the first galaxies and the vast cosmic web we see today. This theory makes a spectacular prediction that the violent stretching of spacetime during inflation should have generated ripples in the very fabric of the cosmos, primordial gravitational waves. These waves would have left a faint, swirling pattern, a specific type of polarization known as B modes, imprinted on the cosmic microwave background. Hunting for this signature is one of the most intense pursuits in modern cosmology, with experiments like BICEP and the Planck satellite scanning the ancient sky for this ghostly fingerprint of creation. So we are left to wonder what was the ultimate trigger for this incredible event. Could the same conditions that launched our universe into existence arise again, sparking new cosmic bubbles in an infinite, ever-growing multiverse? The answer lies in understanding the very first forces that shaped reality, forces that may have begun their existence in a state of perfect and unstable symmetry. That initial burst of inflation filled the universe with a searing, energetic soup, a perfect balance of particles and their mysterious counterparts, antiparticles. For every particle of matter created, an antimatter twin was born. This should have been the universe's ultimate undoing. When matter and antimatter meet, they annihilate each other in a flash of pure energy, leaving behind nothing but radiation. According to this perfect symmetry, the early cosmos should have consumed itself, leaving a vast, empty void of light. And yet, here we are, in a universe filled with galaxies, stars, planets, and us. Everything we see is made of matter, so where did all the antimatter go? This is the profound puzzle of the matter-antimatter asymmetry, one of the most fundamental questions in all of physics. Somehow, in the first moments of existence, a tiny, almost imperceptible imbalance must have occurred. For every 1 billion antimatter particles, there were 1 billion and 1 matter particles. That 1 in a billion excess is all that survived the Great Annihilation. Everything that constitutes our visible universe is the leftover ash from that primordial battle. The process that created this slight preference for matter is known as baryogenesis. In the 1960s, the brilliant physicist and dissident Andrei Sakharov outlined the 3 essential conditions needed for this to happen. The universe had to be out of thermal equilibrium. It had to allow for processes that treated matter and antimatter differently, and it had to violate a principle known as charge parity symmetry, or CP symmetry. This last condition is the most mind-bending. CP symmetry is the idea that the laws of physics should be the same if you simultaneously swap a particle with its antiparticle, which is charge conjugation, C, and view its reflection in a mirror, which is parity, P. It is a fundamental expectation of a fair and balanced cosmos, but our universe, it seems, is not perfectly fair. We have observed CP violation in the delicate decays of certain subatomic particles like kaons and B mesons in laboratory experiments. In these decays, matter and antimatter behave in subtly different ways, breaking the mirror. The problem is, the amount of CP violation we have measured is far too small to account for the overwhelming dominance of matter in the cosmos. It is like finding a single coin on the street when you need to explain a mountain of gold. This forces physicists to look for new, more powerful sources of symmetry breaking. Experiments at the Large Hadron Collider are meticulously studying the behavior of particles and antiparticles, hunting for any tiny discrepancy that could solve the mystery. Another promising avenue involves the ghostly neutrino. We now know that neutrinos oscillate, changing their identity as they travel through space. If neutrinos are their own antiparticles, a special class of particles known as Majorana fermions, then their oscillations could involve processes that violate CP symmetry on a grand scale, potentially generating the matter excess we see today. So we are left to reflect on a staggering implication. Our entire existence hinges on a broken symmetry, a fundamental bias written into the laws of physics at the dawn of time. What does this cosmic favoritism for matter tell us about the universe's initial conditions? Was it a random fluctuation, or the signature of a deeper law we have yet to uncover? This foundational asymmetry, which allowed something to emerge from nothing, finds a strange echo in another broken symmetry, one that governs the very arrow of time itself. That broken symmetry which allowed our existence now confronts a number so colossal it defies human comprehension. We have met the cosmological constant, Einstein's term for the energy of empty space, which drives the accelerating expansion of the universe. The problem is not its existence, but its size. When physicists calculate the expected energy density of the vacuum using the well-tested rules of quantum field theory, they arrive at a staggering result. The predicted value is larger than the observed value of dark energy by a factor of 1 followed by 120 zeros. This is not just a little off. It is the single worst theoretical prediction in the entire history of science. To grasp the scale of this error, imagine calculating the distance to the moon and getting an answer smaller than the width of a single atom. The cosmological constant problem represents a fundamental disconnect between our two most powerful theories, general relativity and quantum mechanics. Quantum mechanics tells us that the vacuum of space is not empty at all. It is a seething, bubbling foam of virtual particles, constantly popping in and out of existence. These quantum fluctuations should endow every cubic centimeter of empty space with a tremendous energy density, producing a repulsive gravitational effect so powerful that it would have ripped the universe apart before stars or galaxies could ever form. Yet, when we look through our telescopes, we see a universe that is expanding only relatively gently. The observed cosmological constant is incredibly small, but not quite zero. Why don't these violent vacuum fluctuations produce the catastrophic gravitational push that our math demands? The physicist Steven Weinberg once considered a radical possibility. Perhaps the constant is not determined by a beautiful equation, but by a simple, stark requirement. If it were any larger, the universe would expand too quickly for galaxies to coalesce and for life to ever arise. This is the anthropic principle. It suggests that in a vast multiverse, where every possible value of the constant is realized, we inevitably find ourselves in one of the rare universes where the numbers are just right for our existence. For some, this is a compelling, if unsettling, explanation. For others, it feels like a surrender, an admission that we may never find a deeper reason. This problem strikes at the very heart of physics, challenging our hope for a final, unified theory. It forces us to ask a deeply reflective question. Is our universe exquisitely fine-tuned for life by chance? Or is this immense discrepancy screaming that we are missing a fundamental piece of the puzzle, a theory that seamlessly merges the cosmos of gravity with the quantum world? The answer likely lies in understanding the quantum nature of gravity itself, a force that remains stubbornly outside our current framework. This profound disconnect between the quantum world and cosmic gravity finds its ultimate expression in a phenomenon so bizarre it troubled Einstein himself. He called it spooky action at a distance. We know it as quantum entanglement. Imagine two particles born from the same event, like twin photons. Their properties, such as their spin or polarization, are linked or entangled. No matter how far apart they travel, even if they are separated by the width of a galaxy, measuring one particle instantly determines the state of the other. This connection appears to happen faster than light, directly challenging the cosmic speed limit set by relativity. For Einstein, this was unacceptable. He believed there must be some hidden, local variable we had not yet discovered, a secret instruction set telling each particle how to behave. He insisted that reality must be local, meaning no physical influence can travel faster than light. Quantum mechanics, with its spooky action, seemed to violate this fundamental principle. Decades later, physicist John Bell devised a way to test Einstein's hidden variable theory. Bell's theorem provided a mathematical framework for an experiment. If local hidden variables were real, then the correlations between the particles' measurements would fall within a certain limit. If quantum mechanics was correct, the correlations would exceed that limit. When physicists finally performed these delicate experiments, the results were unequivocal. Quantum mechanics 1. Entanglement was real and no local hidden variable theory could explain it. The particles are truly connected in a way that transcends space. This has profound implications. It is the foundation for emerging technologies like quantum cryptography, where any attempt to eavesdrop on a message instantly disturbs the entangled link, revealing the intrusion. It is the engine for quantum computers, which could solve problems in minutes that would take classical computers millennia. But how does this play out on a cosmic scale? Astronomers have performed a breathtaking version of Bell's test using light from distant quasars. They created entangled photon pairs here on Earth, then used the ancient light from quasars billions of light years away to decide which property of the entangled photons to measure. By using the cosmos itself as a random number generator, they aimed to close any possible loopholes. The result once again confirmed the spooky action. Quantum entanglement holds firm even across astronomical distances. This forces us to confront a deep puzzle. How can these instantaneous correlations exist in a universe governed by relativity, where nothing can outtrace a beam of light? The resolution is subtle but crucial. While the correlation is instantaneous, no usable information, no signal, can be sent faster than light. You cannot control the outcome of your measurement, so you cannot send a message to your partner on the other side of the galaxy. The universe maintains its speed limit for communication, but behind the scenes, reality is deeply, mysteriously interconnected. So we must ask, what is the true nature of this quantum link that weaves through the cosmos? Does it hint at a deeper layer of reality where separation is an illusion? This strange interconnectedness finds one of its most extreme tests at the edge of another cosmic mystery, where space and time cease to exist. This strange interconnectedness finds one of its most extreme tests at the edge of a black hole, where the two pillars of modern physics, general relativity and quantum mechanics, wage a war with no clear winner. The battlefield is the black hole information paradox, a conflict over the ultimate fate of reality itself. According to Einstein's theory of general relativity, the event horizon of a black hole is a point of no return. Anything that crosses this boundary, whether a star, a planet, or a book, is lost forever, crushed into the singularity at the center. The information about what fell in, the specific arrangement of atoms that made that object unique, is seemingly erased from our universe. This presents a catastrophic problem for quantum mechanics, which holds a sacred principle called unitarity. This principle states that information is never truly lost. It can be scrambled, transformed, or hidden, but it must, in principle, be recoverable. If information can be permanently destroyed inside a black hole, then quantum mechanics, our most successful theory of the small, is fundamentally wrong. The crisis was ignited by Stephen Hawking. He combined quantum theory with the curved space around a black hole and made a stunning prediction. Black holes are not completely black. They emit a faint glow of radiation, now known as Hawking radiation. This radiation slowly saps the black hole's energy, causing it to shrink and over eons evaporate completely. Hawking initially concluded that this radiation was purely thermal, a random heat noise. It carried no information about what had fallen in. He famously made a bet with physicists Kip Thorne and John Preskill, declaring that information swallowed by a black hole is lost forever. If Hawking was right, then when the black hole finally evaporates, the information about all the things it consumed is gone, violating the core tenet of quantum mechanics. This is the heart of the paradox. How can our universe be both quantum mechanical and allow for information to vanish into a black hole? It cannot. One of these foundational theories must break. The search for a resolution has spawned some of the most mind-bending ideas in physics. One revolutionary concept is the holographic principle. It suggests that all the information about what is inside a three-dimensional black hole is actually encoded on its two-dimensional event horizon, like a cosmic fingerprint smeared across the surface. Just as a hologram on your credit card stores a three-dimensional image on a two-dimensional film, the black hole stores the information of its contents on its boundary. Then, as Hawking radiation escapes, it could, in theory, carry that encoded information back out into the universe. This idea led to another radical proposal, the black hole firewall. If information is to be preserved, the event horizon might not be the smooth, uneventful space Einstein predicted. Instead, it could be a searing wall of high-energy particles, a violent boundary that instantly incinerates anything that crosses it. This would resolve the information paradox, but at a terrible cost, violating the principle that an observer falling into a black hole should notice nothing special as they cross the horizon. At the core of these modern solutions lies quantum entanglement. Hawking radiation is created when a pair of entangled virtual particles pops into existence near the event horizon. One particle falls in while its entangled partner escapes as radiation. For information to be saved, the entanglement relationships must be carefully transferred, a complex quantum dance that preserves the total information. This concept, known as black hole complementarity, suggests that from the perspective of an outside observer, information never falls in, it is smeared on the horizon. But from the perspective of someone falling in, they pass through smoothly. Both views can be correct, complementing each other, because no single observer can ever see both stories unfold. So we are left with a profound question. Is the universe a perfect recorder, preserving every bit of information in a holographic code? Or does the immense gravity of a black hole truly have the power to erase the past? The answer will force us to rewrite our understanding of reality, pushing us to ask what space-time is truly made of when information itself is the most fundamental currency. That profound question of what reality truly is, of whether information can be erased, leads us directly to the ultimate breakdown point, the black hole singularity. General relativity makes a stunning and terrifying prediction. Deep within a black hole, at its very center, all the matter it has consumed is crushed into a single point of infinite density, a place where the very concepts of space and time cease to have any meaning. This is the singularity, a point where the known laws of physics simply break down. The equations of Einstein's theory produce infinities, a clear signal that our understanding is incomplete. The great physicist Roger Penrose proved, through his singularity theorems, that such a point of no return is an inevitable consequence of gravitational collapse under certain conditions. Once a sufficient amount of matter collapses under its own weight, the formation of a singularity is unavoidable. This presents a fundamental challenge, a screaming demand for a new theory that can marry gravity with quantum mechanics. To resolve the paradox of the singularity, we must understand the fabric of space-time on the smallest possible scales. One proposed solution is the cosmic censorship hypothesis. This idea, also championed by Penrose, suggests that nature abhors a naked singularity. The proposal is that every singularity is always hidden from our view, forever cloaked behind an event horizon. This cosmic veil protects the outside universe from the unpredictable chaos and the breakdown of causality that would occur if we could ever directly observe such a point. It is a cosmic rule that preserves the orderly physics we rely on outside the black hole's grip. But what if the singularity is not truly a point of infinite density? The leading candidates for a theory of quantum gravity offer fascinating alternatives. In loop quantum gravity, for instance, the intense gravity at the center of a black hole could be counteracted by a powerful repulsive force arising from quantum geometry. Instead of collapsing to infinity, the matter might undergo a quantum bounce, potentially spewing it out into a new region of spacetime, perhaps even giving birth to a new universe. String theory, on the other hand, suggests that what we call a singularity might actually be a dense, vibrating knot of fundamental strings, a fuzzball with a complex internal structure that prevents the formation of a true point of infinite density. Consider the supermassive black hole at the center of our own Milky Way galaxy, Sagittarius a star. We have mapped the stars whipping around its invisible center, confirming its immense gravitational pull. We know the singularity is there, according to our best models, a silent mathematical ghost at the heart of our cosmic home, yet we have no way of knowing what it truly is. Is it a gateway, a bounce, or a final end to physics itself? So we are left to ponder the ultimate question: what actually lies at the heart of a black hole? The answer to this enigma does not just apply to the end of stars, it connects directly to the very beginning of everything. For if our universe exploded outward from a state of extreme density and temperature, then the Big Bang itself may have been the ultimate singularity, a moment where all of reality was compressed into a single point. Understanding what happens at the center of a black hole could be the key to unlocking the origin of our entire cosmos. This journey from the infinitesimally small beginning of the universe leads our gaze outward to the largest structures ever discovered, where the rules of gravity are tested on an entirely different scale. From the silent heart of our galaxy, we face a universe that should be teeming with voices. With billions of Earth-like planets orbiting in the habitable zones of stars, the cosmos appears to be a perfect nursery for life. Yet when we listen, we hear only an immense, profound silence. This is the Fermi Paradox, the staggering contradiction between the high probability of extraterrestrial civilizations and the utter lack of any evidence that they are out there. The question was famously posed by physicist Enrico Fermi during a casual lunch conversation in 1950. Looking at the vast number of stars and the age of the galaxy, he asked a simple, devastating question. Where is everybody? If life is common, then some civilizations should be millions of years older than our own. Their engineering projects should be visible across interstellar space. The galaxy should be buzzing with their signals and their ships, but the sky is empty. This silence is one of the most haunting mysteries in all of science. To frame the problem, astronomer Frank Drake created his famous equation, a way to estimate the number of communicative civilizations in our galaxy. The equation multiplies a series of factors: the rate of star formation, the fraction of stars with planets, the number of habitable worlds per system, the fraction where life actually emerges, the fraction where life becomes intelligent, the fraction that develops technology to broadcast its existence, and finally, the length of time such a civilization lasts. The result is a number, n. Plug in optimistic values and the galaxy should be crowded. Plug in pessimistic ones and we might be utterly alone. The terrifying possibility is that one of these factors is almost zero. This is the core of the Great Filter hypothesis. It suggests that there is some monumental barrier, a step in the evolution of life that is incredibly difficult to overcome. This filter could lie in our past. Perhaps the origin of life itself is a fantastically rare fluke. Or maybe the jump from simple single-celled organisms to complex multicellular life is the true bottleneck. If the Great Filter is behind us, it would explain why we see no one else. We were the lucky ones who made it through. The more chilling prospect is that the Great Filter lies in our future. Perhaps every advanced civilization eventually discovers a technology, whether nuclear war, engineered pandemics, or runaway artificial intelligence, that leads inevitably to its own self-destruction. In this scenario, the silence of the cosmos is a grave warning, a preview of our own destiny. Other solutions are less apocalyptic but equally mind-bending. Perhaps spacefaring civilizations are common, but they exist in ways we cannot perceive. They might have transitioned to a post-biological state, living as super-intelligent machines in simulated realities, with no interest in the physical universe. Or maybe we live in a cosmic zoo, a designated wilderness area where advanced beings observe us under a strict policy of non-interference. The universe itself might also be actively hostile to long-lived civilizations. Cataclysmic events like gamma-ray bursts could periodically sterilize large swaths of the galaxy, resetting the evolutionary clock before any civilization can become interstellar. The sheer scale of space and time presents another immense hurdle. The distances between stars are so vast that even at a significant fraction of the speed of light, a voyage to the nearest star would take decades. The energy required is astronomical, and even if a civilization mastered interstellar travel, would they bother to visit a quiet, average solar system like ours? Communication is no easier. Our own radio bubble, the sphere of human-made signals expanding out from Earth, is only about 100 light-years across, a tiny bubble in a galaxy 100,000 light-years wide. An alien signal might have washed over Earth and faded away millions of years before we even learned to use radio waves, so we are left staring at the stars, confronted by a profound choice. Is our existence a glorious, singular accident in a lifeless void, or are we simply a young species in a galaxy filled with ancient, silent watchers? The answer to this paradox will tell us not just about them, but about our own place in the cosmos and the ultimate fate of all intelligence. This contemplation of our cosmic solitude naturally shifts our perspective to the very laws that govern our existence, prompting us to ask why those laws seem so perfectly tuned for life in the first place. That profound silence is suddenly broken by a blast. In 2007, astronomers sifting through old data from a radio telescope in Australia found something astonishing: a spike of radio energy so intense it saturated their equipment. It lasted just 5 milliseconds, a blink of an eye, but in that instant it released more energy than our sun puts out in 80 years. This was the first detected fast radio burst, an event that seemed to come from another galaxy. Since then, we have recorded hundreds of these fleeting, colossal explosions, each one a brief, brilliant flash in the cosmic radio static. They arrive without warning from random points in the sky, their sources often billions of light-years away. Their brevity is the core of the mystery. How can any natural object generate such staggering power and release it all in less time than it takes you to blink? The hunt for their origin is like cosmic forensics, with astronomers scrambling to point the world's most powerful telescopes at the location of a burst the moment it is detected, hoping to catch an afterglow or identify its host galaxy. The challenge is immense. Duncan Lorimer, one of the astronomers who discovered the first burst, described it as trying to solve a jigsaw puzzle where you only get one piece at a time, and the pieces are arriving from billions of light-years away. To trace their cosmic journey, scientists use a clever trick called the dispersion measure. As the radio waves travel through the sparse gas between galaxies, higher frequencies arrive at our telescopes slightly before the lower frequencies. The amount of this smear, this dispersion, tells us how much material the signal has passed through, providing a rough estimate of its mind-boggling distance. The true nature of these bursts has only become more puzzling with the discovery of repeaters. While most FRBs are one-off events, a few, like the famous FRB 121102, fire off again and again from the same patch of sky. This ruled out cataclysmic, one-time events like a star exploding or two black holes merging. the source had to be something that could survive its own violent outburst. The leading suspect is a magnetar, a type of neutron star with a magnetic field so powerful it could erase the data on every credit card on Earth from halfway to the moon. A starquake on such an object, a sudden cracking of its rigid crust, could theoretically unleash a firestorm of radio waves. Other theories are even more exotic. Could it be the result of an asteroid colliding with a neutron star, the immense gravitational energy of the impact converted into a radio scream? Or perhaps it is the death spiral of a star being shredded by a black hole? The sheer power and brevity of the signals have, inevitably, led to more speculative ideas. Could they be artificial, the leakage from unimaginably powerful interstellar transmitters, or even the light sails of alien spacecraft being pushed across the galaxy by giant radio beams? While most astronomers consider natural explanations far more likely, the very possibility forces us to confront the extreme limits of known physics. What cosmic engine can switch on and off in milliseconds, operating with a power that dwarfs entire stars? These bursts are more than just curiosities, they are probes. By studying how their signals are twisted and altered on their long journey to Earth, we can map the invisible, diffuse matter that floats in the vast voids between galaxies. Each one is a fleeting flashlight illuminating the dark cosmic web. Their unpredictable nature reminds us of a universe that is dynamic and violent, where the sky is filled with transient events we are only beginning to perceive. The same radiostatic that hides fast radio bursts occasionally tears open, revealing a far more violent flash. Gamma-ray bursts are the most powerful explosions the universe has produced since the Big Bang itself. In just a few seconds, a single GRB can release more energy than our Sun will emit over its entire 10 billion-year lifetime. These are not mere flashes in the dark, they are cosmic cataclysms of almost unimaginable scale. For decades, they were one of astronomy's greatest secrets, first detected by military satellites watching for nuclear tests on Earth. Instead, they found the sky lighting up with these colossal, unpredictable explosions from deep space. The late astrophysicist Neil Gehrels, a pioneer in the field, described the moment of detection as a revelation, a signal so powerful it saturated the instruments designed to watch for the end of the world. His work led to satellites like Swift, which can swivel with lightning speed to pinpoint a burst's location and alert telescopes across the globe in seconds, transforming these fleeting events from mysteries into objects of intense study. We now know these bursts come in two distinct flavors, each with its own terrifying origin story. Long gamma-ray bursts last for more than 2 seconds, and they are the death cries of the most massive stars in the universe. When such a star, a true behemoth, exhausts its nuclear fuel, its core collapses not into a neutron star, but directly into a black hole. As it falls, the infalling matter doesn't just vanish. It is funneled by intense magnetic fields into two narrow, oppositely directed jets that punch their way out of the star at nearly the speed of light. The GRB itself is the brilliant, focused beam of this relativistic jet, and if that jet is pointed at Earth, we see the full, terrifying power of the stellar death. The collapsing star itself then explodes as a supernova, a colossal blast that is utterly dwarfed by the energy of the jet. The other type, short gamma-ray bursts, last less than 2 seconds and are even more violent in concept. They are thought to be the final, furious embrace of two ultra-dense stellar corpses, like neutron stars or a neutron star and a black hole. As these massive objects spiral together over millions of years, they finally merge in a cataclysmic collision, shaking the fabric of space-time and unleashing a similar, though shorter, blast of gamma rays. These events are not just spectacular, They are cosmic laboratories that challenge our understanding of physics at its most extreme. How can a stellar collapse or a merger accelerate particles to such incredible energies, creating photons of light that are billions of times more energetic than visible light? The physics of these relativistic jets pushes our models of plasma and magnetism to the absolute breaking point. One of the brightest bursts ever recorded was GRB 130427A. Detected in April 2013, it was so powerful that its afterglow remained visible to large amateur telescopes for hours. It came from a relatively nearby galaxy, a mere 3.6 billion light-years away, and for a moment, it was the most distant object visible to the naked eye. Its intensity provided a treasure trove of data, revealing details about the jet's composition and the staggering magnetic fields involved. Beyond their scientific value, gamma-ray bursts hold a more ominous significance. They are potential life-extinguishing events on a galactic scale. If a long GRB were to occur within a few thousand light-years of Earth, and its deadly jet were pointed directly at us, the effects would be apocalyptic. The initial blast of radiation would scour our planet's atmosphere, destroying the ozone layer that protects us from solar ultraviolet radiation. The sky would glow with a second sun of deadly X-rays and gamma rays, triggering chemical reactions that would produce a brown, smog-filled sky, initiating a global winter that could last for years. It is believed that such an event may have been responsible for one of the major mass extinctions in Earth's distant past. The universe is not just a beautiful spectacle, it is also a dangerous place, capable of wiping the slate clean with a random flash from across the galaxy. So we are left to wonder what cosmic engines born from stellar death and destruction can produce such focused, violent outbursts that they can be seen across the universe and threaten life itself. The answer lies in the final, frantic moments of the most massive objects in existence. That same cosmic violence that creates gamma-ray bursts also launches a different kind of messenger, one that strikes our own planet with unimaginable force. A constant rain of particles from deep space bombards our atmosphere, a silent drizzle of atomic shrapnel known as cosmic rays. Most are simple protons or atomic nuclei, but a rare few carry energies so colossal they defy belief. These are the ultra-high energy cosmic rays, and they hit our sky with a punch millions of times greater than anything the most powerful human-built particle collider can produce. The physicist Pierre Auger, who pioneered their study, once marveled that these particles must come from what he called the violent universe. The vast observatories that now scan the skies for them bear his name, hunting for the faint blue flashes these rays create when they smash into the air above us. The existence of these particles presents a profound paradox known as the GZK Cutoff. This theoretical limit, named for Greisen, Zatsepin, and Kuzmin, states that any proton with such tremendous energy should not be able to travel very far through space. It would inevitably collide with the photons of the cosmic microwave background, the leftover glow from the Big Bang. In such a collision, the proton would lose a huge amount of its energy, creating new particles and slowing down long before it could ever reach Earth from a distant source. The universe, it seems, should have a built-in speed limit for these cosmic projectiles, yet we keep detecting them. The most famous example is the so-called "Oh my God" particle, detected in 1991 over Utah. This single subatomic particle, likely a proton, carried the kinetic energy of a well-thrown baseball, all compressed into a tiny speck moving at 99.9999999999996% of the speed of light. It was an energy level thought to be impossible for a particle from beyond our galaxy. So what cosmic particle accelerator is powerful enough to defy the GZK cutoff and fire such a bullet across the universe? The suspects are the most energetic objects we know, active galactic nuclei where supermassive black holes devour matter and blast out jets of plasma could potentially focus particles to these energies. The remnants of supernova or the mergers of neutron stars might also act as natural cyclotrons, using swirling magnetic fields to whip particles to near light speed. The mystery deepens because these ultra-high energy cosmic rays do not point directly back to their source. They are charged particles, so their paths are bent and twisted by the magnetic fields that perm the galaxy. It is like trying to trace the origin of a bullet that has been ricocheting inside a house of mirrors. This is why observatories like the Pierre Auger Observatory in Argentina use thousands of detectors spread over 3,000 square kilometers, an area the size of Rhode Island, to catch the extensive air showers these particles create, hoping to triangulate their direction. The search for their origin is not just about understanding cosmic accelerators, it also intersects with the hunt for dark matter. Some theories suggest that the decay or annihilation of certain hypothetical dark matter particles could produce a signature flux of high-energy cosmic rays. So every time one of these incredible particles slams into our atmosphere, it is more than just a record-breaking event. It is a clue, a piece of evidence pointing to the most powerful and secretive engines in the cosmos. How does nature accomplish what our greatest technology cannot, flinging single particles with the force of a major league pitch? The answer is written in the silent, invisible rain that has fallen upon our world since its very beginning. Our galaxy is not drifting aimlessly through the void. We are caught in a current pulled by an immense and invisible force. The Milky Way, along with our entire local group of galaxies, is racing at over 2 million kilometers per hour toward a specific point in the constellation Centaurus. This mysterious destination is known as the Great Attractor, a colossal gravitational anomaly whose true nature is veiled from our view. It lies directly behind the crowded plane of our own galaxy, a region astronomers call the zone of avoidance. Here, the gas, dust, and stars of the Milky Way's central bulge create a cosmic blind spot, blocking our optical view of the universe beyond. Astronomer René Cron-Courtoueg described the frustration and the challenge of trying to map the cosmos through this obscuring curtain. To see through the galactic dust, scientists had to turn to different eyes on the sky, using infrared telescopes that sense heat and radio telescopes that can pierce the murk. These surveys slowly revealed the shadowy outline of the Great Attractor, not as a single object, but as a vast concentration of mass, a gravitational focal point pulling in thousands of galaxies. The pull we feel is the collective gravity of an enormous knot of dark matter and dozens of rich galaxy clusters all clumped together. Yet, even when we account for all the visible galaxies and their dark matter halos in that region, the math still falls short. The sheer strength of the attraction suggests there is even more mass there than we can find, pointing to a deeper enigma embedded within the cosmic web. This mystery only expanded when, in 2014, a team of astronomers mapped the motions of galaxies on an even grander scale. They discovered that the Great Attractor is not the ultimate destination, but merely a waypoint. It acts as the gravitational center of a much larger structure, a supercluster of galaxies they named Laniakea, a Hawaiian word meaning immense heaven. Our entire local group, the Great Attractor, and 100,000 other galaxies are all part of this single, flowing river of matter, all moving together within this cosmic continent. Picture the universe not as a static collection of islands, but as a dynamic landscape of flowing rivers. Our galactic neighborhood is like a leaf caught in a slow, cosmic current, flowing toward a grand, unseen waterfall. We can feel the pull of the current, and we can map the other leaves moving with us, but the ultimate source of the flow remains hidden in the distance. So what immense, unseen structures beyond Laniakea are ultimately sculpting this vast cosmic motion? And where is this great river of galaxies truly leading us? Our cosmic journey toward the Great Attractor suggests a universe with a hidden structure, and that very idea finds a ghostly signature in the oldest light we can see. The cosmic microwave background radiation, that pristine baby picture of the universe, holds a strange and unsettling alignment. When scientists from the Planck mission mapped its faint temperature variations with exquisite precision, they expected a random, speckled pattern in every direction, a final confirmation of the cosmological principle that the universe is isotropic, the same in all directions. Instead, they found something that made them give it a dramatic name: the axis of evil. The largest temperature fluctuations, the low-order multipoles like the quadrupole and octupole, are not randomly oriented. Their hot and cold spots appear to be aligned with each other and with the plane of our own solar system, pointing toward a specific axis in space. This is a profound and unexpected violation of isotropy. It suggests the universe might have a preferred direction, a cosmic north that challenges our most basic assumptions. Planck scientist Paolo Natoli noted that while the statistical significance is not overwhelming, the alignment is stubbornly there, a persistent anomaly that refuses to be explained away by known systematic errors or galactic foregrounds. One way to visualize this is to think of the CMB as a faint sound humming through the cosmos. We expected to hear pure noise, a chaotic symphony from all directions. But instead, we detect a faint, coherent chord, a single note that seems to resonate along one specific axis across the sky. The quadrupole, which describes the most basic oval-shaped distortions, and the octupole, a more complex three-lobed pattern, are mysteriously synchronized. Their axes line up in a way that has only a few % probability of happening by pure chance. What could possibly cause such an alignment in the primordial universe? One radical possibility is that it is a fossil, a pre-inflationary relic from a time before the universe blew up. Perhaps the fabric of spacetime itself has a subtle, crystalline structure that imprinted this directionality onto the cosmos at its birth. Another idea points to cosmic topology, suggesting the universe is not infinite but has a finite, multiply-connected shape, like a hall of mirrors on a cosmic scale. Light traveling through such a twisted geometry could create the illusion of large-scale alignments, or perhaps immense, universe-spanning magnetic fields, generated in the earliest moments, could have stretched and oriented these primordial fluctuations. The axis of evil forces us to confront a deeply unsettling question. Does our universe have a fundamental handedness, a spin or a drift written into its very foundation that we are only now beginning to perceive? If the cosmos is not the same in every direction, what other fundamental symmetries might be broken, and what does that say about our place within it? This hint of a cosmic axis pulls our gaze from the largest scales to the smallest, where the very particles that build reality might be connected to this primordial directionality through their own mysterious spin. This subtle axis in the cosmic background radiation is not the only crack appearing in our model of the universe. A far more direct and pressing conflict has emerged over one of the most fundamental numbers in all of cosmology, the Hubble constant. This number describes how fast the universe is expanding today, the current rate at which galaxies are receding from each other. For years, we assumed we had a good handle on it, but now, two of the most precise methods ever devised for measuring it are giving us starkly different answers. This disagreement is known as the Hubble Tension, and it is not a small statistical fluke. It is a gaping discrepancy that points toward a potential crisis in our understanding of cosmic history. Nobel laureate Adam Rees, whose work on supernova first revealed the accelerating universe, has called this tension a real problem, one that likely requires new physics to resolve. The conflict is between two ways of seeing the cosmos. One method looks back to the infant universe, using the exquisitely detailed map of the cosmic microwave background from the Planck satellite. By analyzing the subtle patterns in this primordial light, physicists can extrapolate the universe's expansion history forward in time to predict what the Hubble constant should be today. It is like calculating the current speed of a car by studying a detailed photograph taken at the very start of its journey. The other method, led by the SH0ES project, looks at the local, modern universe. It uses a cosmic distance ladder, carefully building from parallax measurements of nearby stars to the predictable brightness of Cepheid variable stars, and finally to the brilliant flashes of Type Ia supernova in relatively close galaxies. This measures the expansion rate directly, right now, like reading the car's speedometer. The problem is, the speedometer and the calculated speed from the starting photo do not match. The local measurements from supernova give a faster expansion rate, while the early universe data from Planck gives a slower one. The difference is only a few kilometers per second per megaparsec, but in the world of precision cosmology, this is a massive chasm, a disagreement of several sigma, meaning it is extremely unlikely to be a simple error. It is as if you carefully mapped a road trip and predicted you should be going 60 miles per hour, but your speedometer insists you are going 73. One of them is wrong, or more intriguingly, the rules of the road have changed along the way. So what could cause this discrepancy? Perhaps there is an unknown ingredient in the early universe. One compelling idea is early dark energy, a strange form of energy that may have briefly surged and altered the expansion rate in the universe's first few 100,000 years, throwing off the Planck extrapolation. Or maybe neutrinos, those ghostly particles that flood the cosmos, have properties we have not yet accounted for, perhaps being slightly more massive than we thought, which would affect how structures clump together and evolve. Some have even suggested that dark energy itself is not constant but evolving, growing stronger over time. The Hubble tension forces a profound and humbling question upon us. Is our cherished standard model of cosmology, the lambda CDM model, which has been so successful for decades, fundamentally incomplete? Are we missing a crucial chapter in the story of the cosmos? A chapter that would explain why the universe's early past and its present are telling us two different stories about its expansion. This is not just a debate over a number, it is a direct challenge to our most basic narrative of cosmic evolution. That same cosmic expansion history, now under tension, finds its echo in a mystery written into the very chemistry of creation. The first few minutes after the Big Bang were a frantic forge, a period known as Big Bang nucleosynthesis, where the entire universe was hot and dense enough to fuse the lightest elements. This process successfully predicted the cosmic abundances of hydrogen and helium with stunning accuracy, a cornerstone triumph for the Big Bang model. But for one particular element, the theory gets it dramatically wrong. This is the lithium problem. Our best models predict that a specific isotope, lithium-7, should be about 3 times more abundant in the oldest stars than what we actually observe. When we look at the atmospheres of ancient stars in the halo of our galaxy, which have preserved their primordial composition, we find only about 1/3 of the lithium that our equations insist must be there. It is as if a cosmic thief systematically stole this light element from the nursery of the universe. Cosmologist Brian Fields has described this discrepancy as a persistent and stubborn puzzle. one that refuses to go away despite decades of scrutiny. Where did all the lithium go? One possibility is that our understanding of the nuclear physics itself is incomplete. Perhaps the reaction rates involving beryllium-7, which decays into lithium-7, are slightly different under those extreme primordial conditions than we have calculated in our laboratories. Even a tiny miscalibration could resolve the entire issue, but after years of refined experiments, the nuclear data seems solid, pointing the finger elsewhere. A more exotic solution involves the shadowy realm of particle physics. What if unknown particles born in the early universe interacted with the primordial soup and destroyed the lithium? A prime candidate is the sterile neutrino, a hypothetical heavier cousin of the standard neutrino that barely interacts with normal matter. If these particles existed, they could have decayed in specific ways, producing radiation that would have broken apart the fragile lithium nuclei after they formed. Other speculative ideas involve actions or even the decay of supersymmetric particles, each offering a different pathway to disintegrate the excess lithium. The hunt for an answer is a race between two frontiers, the immense scale of cosmology and the ultra-precise world of nuclear physics. Solving the lithium problem is not just about correcting a number in a table. It is a direct test of our understanding of the universe's first nuclear furnace. If the solution requires new particles, it would be a monumental discovery, a crack in the standard model of particle physics revealed by the ancient light of the first stars. So we are left to ponder a simple yet profound question. How can the measured amount of a single, simple element in the oldest stars challenge the entire story of our cosmic origins? The answer is written in the faint spectral lines of ancient suns, a chemical fingerprint from the dawn of time. Far out in the cold dark of the outer solar system, two robotic explorers began to slow down for no apparent reason. The Pioneer 10 and 11 spacecraft, having completed their historic missions to Jupiter and Saturn, were coasting toward the edge of our planetary neighborhood. Yet as scientists tracked their paths over decades, a tiny, persistent drift appeared in their trajectories. They were falling ever so slightly behind schedule, as if an invisible hand was gently applying a constant, minuscule brake. This was the Pioneer Anomaly, a deviation so small it was like measuring the width of a human hair from a mile away, but for physicists it was a signal they could not ignore. Mission scientist John Anderson described it as a ghost in the data, a whisper of something wrong with our understanding of gravity itself. For years, this unmodeled sunward acceleration fueled speculation about new physics, from modifications to Einstein's theory of general relativity to the gravitational pull of unseen dark matter. The leading explanation, after a monumental effort of data archaeology and modeling, pointed to something far more mundane, yet brilliantly complex thermal radiation pressure. The plutonium power sources on board generated heat that was constantly radiated away from the spacecraft. This emission was not perfectly symmetrical. A tiny fraction more heat was emitted from the back of the spacecraft's main dish antenna than from the front, creating a net push back toward the sun, a photon break that perfectly accounted for most of the anomalous deceleration. It was like a car slowing down because its own engine was radiating a faint, constant breeze backward. While this solution resolved the bulk of the mystery, some tiny discrepancies stubbornly remain in the data, leaving a sliver of doubt. The decades-long hunt for the cause of the Pioneer Anomaly demonstrates a profound truth about exploring the cosmos. Sometimes the most subtle, unexpected glitches in the data can be the most revealing. What other tiny deviations in the motion of our spacecraft, hidden in the noise, might be whispering secrets about the fundamental fabric of the universe? This meticulous attention to orbital minutiae leads us directly to another, far more significant gravitational puzzle, one that involves the precise timing of dead stars. The same meticulous tracking that solved the Pioneer puzzle has revealed another, more fleeting gravitational ghost. When spacecraft perform a gravitational slingshot around Earth, using our planet's momentum to fling themselves toward distant targets, their speed undergoes a subtle but measurable shift that no one can fully explain. This is the Fly-by Anomaly. During these high-stakes maneuvers, probes like Galileo or Rosetta have been clocked gaining or losing a few millimeters per second in velocity compared to our most precise predictions. Aerospace engineers working with NASA, a deep space network, have described the bewilderment of seeing their Doppler radar data, a system sensitive enough to detect a snail's pace from millions of miles away, consistently report these tiny, unexpected velocity changes. It is as if an unseen hand gives the spacecraft a faint, additional push or pull during its closest approach. For missions where a millimeter per second error can compound into a thousands of mile miss over an interplanetary journey, this is far from a trivial concern. One of the most dramatic examples was the Near spacecraft's flyby in 1998. As it swung by Earth to gain momentum for its journey to an asteroid, it experienced an unaccounted-for velocity increase of over 13 millimeters per second. Conventional explanations were quickly tested and found wanting. Could it be an error in modeling atmospheric drag? At the altitudes these flybys occur, the atmosphere is a near-perfect vacuum, far too thin to produce such an effect. What about the pressure of solar radiation or the subtle thermal radiation from the spacecraft itself, like the Pioneer Effect? Meticulous calculations showed these forces were orders of magnitude too small. This forces physicists to look toward more exotic possibilities rooted in the fabric of spacetime itself. According to general relativity, a rotating planet like Earth should drag the local spacetime around with it, an effect known as frame dragging. This warping of the inertial frame could, in theory, impart a tiny amount of extra energy to a passing spacecraft. Yet when physicists crunch the numbers, the predicted effect from frame dragging is still too small to explain the full anomaly. Other proposals delve into even more speculative territory, suggesting modifications to gravity itself or the influence of unseen dark matter interactions in Earth's vicinity. The Fly-by Anomaly remains an open case, a whisper of a discrepancy that appears only during a specific, fleeting celestial dance. It challenges the completeness of our gravitational models, not on the scale of galaxies, but right here in our own cosmic backyard. If our understanding of gravity is so exquisitely refined, why does it consistently miss the mark by this tiny yet persistent amount during planetary encounters? These subtle, close-range gravitational puzzles inevitably lead our gaze outward, to the profound and mysterious influence that every planet in our solar system exerts on the Sun. The subtle gravitational tugs felt by our spacecraft point to mysteries much farther out, at the very edge of our planetary neighborhood. Far beyond the orbit of Neptune lies the Kuiper Belt, a vast disk of icy worlds left over from the solar system's formation. For decades, our models predicted this population of frozen objects would continue in a relatively smooth distribution, growing denser for a great distance. But that is not what we see. Instead, at a distance of about 50 astronomical units from the Sun, there is a sudden and dramatic drop, a boundary astronomers call the Kuiper Cliff. It is as if you were walking along a beach expecting the sand to continue, only to find it sheared off into a sheer precipice with nothing but emptiness below. This unexpected boundary directly challenges our most established theories of how the solar system coalesced from its primordial disk. Planetary scientists like Konstantin Batygin have described the cliff as a profound anomaly, a clear sign that our classical models are missing a crucial piece of the puzzle. How was this stark edge carved into the frozen debris of our cosmic backyard? One compelling explanation involves a dramatic event in our solar system's infancy, a close passage by another star in the Sun's birth cluster. The gravitational pull from this stellar intruder could have stripped away the outer material of the Kuiper belt, shearing off the population and leaving behind the cliff we observe today. Another, even more tantalizing idea points to the gravitational hand of an unseen planet, the same hypothetical world often invoked to explain the peculiar clustered orbits of some distant objects. The so-called Planet 9 could also be responsible for this sharp cutoff. Its immense gravity, acting over billions of years, could have cleared out a vast region, sculpting the outer solar system and creating this abrupt frontier. Observing this cliff was a painstaking task, requiring deep sky surveys with powerful instruments like the Subaru telescope in Hawaii. Astronomers methodically scan the heavens, looking for the faint, slow-moving pinpricks of light that betray a distant Kuiper belt object. The data reveals a stark reality. Beyond 50, the number of these detected objects plummets. This is not for a lack of looking. The surveys are sensitive enough to find them if they were there in the predicted numbers. The emptiness is real. This forces us to confront a fundamental question about our home in the cosmos. What hidden force, whether a ghost from our stellar nursery or a giant world lurking in the perpetual twilight, sculpted the final edge of our own solar system? The answer will rewrite the story of our Sun's family and the violent processes that shaped its farthest reaches. That same cliff at the edge of the Kuiper belt is not the final boundary of our Sun's influence. Far beyond it lies a hypothetical shell of icy bodies, a vast and diffuse sphere that marks the true frontier of our solar system. This is the Oort Cloud, a colossal reservoir of frozen cometary nuclei stretching nearly halfway to the nearest star. The existence of this cloud, first proposed by the Dutch astronomer Jan Oort in 1950, was a brilliant inference to explain a cosmic puzzle, the origin of long-period comets. These comets arrive from every direction in the sky on orbits that take millions of years to complete, suggesting a spherical source rather than a flat belt. Oort himself noted that these comets must come from a great swarm of objects at an almost unimaginable distance, a cloud held only by the Sun's faintest gravitational whisper. The challenge is that we have never directly observed an object in the Oort Cloud. The distances involved are so immense that even the largest telescopes struggle to see these dark, frozen worlds. A typical Oort Cloud object might be tens of billions of kilometers away, reflecting only the faintest glimmer of sunlight. Detecting one is like trying to spot a single, dim coal in the pitch black of a cavern miles across. We know the cloud must be there because of the visitors it sends inward. Occasionally, the gravitational nudge of a passing star or the tidal pull of the Milky Way galaxy itself perturbs the delicate orbit of one of these icy bodies. It is like a gentle push on a suspended pendulum, setting it on a new course that sends it falling for thousands of years into the warmth of the inner solar system. A perfect example is Comet Hale-Bopp, which graced our skies in 1997. Its enormous size and brilliantly long tail suggested it was a pristine object on its first visit from the deep freeze of the Oort Cloud, a messenger from the outermost dark. Imagine this vast, unseen reservoir containing perhaps trillions of icy planetesimals, the leftover building blocks of the solar system preserved in a cosmic deep freeze. This leads to a profound question about the limits of our home. Where does our solar system truly end, and where does interstellar space begin? On August 15, 1977, a radio telescope in Delaware, Ohio, recorded a signal so extraordinary that the astronomer reviewing the data simply circled it on the printout and wrote one word in the margin: "Wow." This was the wow signal, a 72-second burst of intense, narrowband radio waves that perfectly matched the predicted signature of an interstellar transmission. It came from the direction of the constellation Sagittarius, ringing with a purity and strength that human technology rarely produces. For that brief minute, it seemed the universe had finally spoken back. Astronomer Jerry Amon's spontaneous annotation captured the sheer astonishment of the moment, a feeling shared by the entire Search for Extraterrestrial Intelligence, or SETI, community. The signal appeared on the hydrogen line frequency, precisely 1420 MHz, a wavelength many scientists consider a logical channel for cosmic communication because hydrogen is the most common element in the universe. The telescope, known as the Big Ear, was fixed to the sky, so the signal rose to a peak and then faded as Earth's rotation carried the antenna's beam away, a perfect bell curve of unknown origin. The hunt was on to find it again, yet despite decades of repeated searches, scanning the same patch of sky with increasingly powerful instruments, the signal never returned. It was a cosmic shout that echoed just once across the gulf of space, leaving only a cryptic mark on a sheet of lined paper. Could it have been a fleeting message from another civilization, a lighthouse beam that swept past our planet and vanished? The search for a natural explanation has been relentless. One proposal suggested it was the reflection of a human-made signal bouncing off a piece of space debris. Another pointed to a pair of comets that happened to be in the same region of the sky at the time, suggesting their hydrogen clouds could have emitted the signal. But these explanations have fallen short. The comets were not in the telescope's beam at the right moment, and the signal's characteristics do not neatly match any known natural celestial source. It remains a singular event, an unlabeled bottle washed up on the shore of our awareness. The wow signal stands as a haunting monument to the central question of the Fermi Paradox. If the cosmos is so vast and so old, why have we heard only one brief and unverifiable whisper? Was it a cosmic dial tone, a random blip from a natural process we do not yet understand, or a postcard from the stars, sent by an intelligence that flickered for just a moment in the dark? That single, unexplained wow from the cosmos finds a modern echo in a star that simply refuses to behave. KIC 8462852, better known as Tabby's star, flickers and dims in ways that no star should. While a distant planet passing in front of its sun causes a predictable, gentle dip in brightness of perhaps 1%, Tabby's star experiences catastrophic drops of up to 22%. These are not the regular, rhythmic shadows of orbiting worlds, but a chaotic sequence of dimming events, some sharp and sudden, others broad and asymmetrical, as if something massive and strangely shaped is drifting erratically through the star's light. The star is named for Tabitha Boyajian, the astronomer who led the team that first brought its bizarre light curve to the world's attention. She described the data as something they had never seen before in any other star, and the initial paper openly asked what in the world was going on. The Kepler Space Telescope, which discovered it, had monitored 150,000 stars, and this one was utterly unique. The strangeness sparked a firestorm of theories, each more incredible than the last. Could it be a vast, fragmented swarm of comets, the aftermath of a planetary collision, or clouds of interstellar dust drifting by? Or, as some dared to speculate, could we be seeing the shadows of an alien megastructure, a partially constructed Dyson swarm designed to harness the star's entire energy output? This last idea, while thrilling, was always a hypothesis of last resort. astronomer Jason Wright, who explored the megastructure concept, was careful to emphasize that it was a testable idea, not a conclusion, and that extraordinary claims require extraordinary evidence. The scientific community mobilized, pointing every available instrument toward the mysterious star. Observations from the ground and space, including crucial data from the Spitzer Space Telescope, began to paint a more detailed picture. They found that the dimming was more pronounced in blue light than in red light. This is a crucial clue, a fingerprint that points toward dust. Small dust particles scatter blue light more effectively, meaning a dusty object passing in front of the star would block more blue light, creating the observed color-dependent dimming. While this strongly favors a natural explanation involving fine, orbiting dust, it does not fully solve the mystery. The central question remains: what is producing such immense, irregular clouds of dust around an otherwise normal star, and in such a bizarre, non-repeating pattern? The story of Tabby's star is also a landmark in how we do science. When traditional funding to monitor the star continuously was unavailable, Tabitha Boyajian and her team turned to the public. They launched a Kickstarter campaign, and thousands of citizen scientists from around the world donated over $100,000, allowing for a dedicated year of observations from a global network of telescopes. This public involvement transformed the star from an academic curiosity into a shared human mystery, so we are left with a profound lesson about discovery in the modern age. When we encounter a signal we cannot immediately explain, our imaginations naturally leap to the most incredible possibilities. Yet the scientific process, aided by the curiosity of millions, patiently sifts through the data, slowly ruling out the impossible to reveal a truth that is often just as strange and wonderful. The lingering mystery of Tabby's star forces us to ask: how do we interpret the cosmic anomalies that defy our current models, and what other stellar oddities are waiting in the data, just one curious pattern away from being found? The cosmic distance ladder, the very framework we use to map the universe, has a wobble in its most crucial rung. For over a century, a specific class of stars known as Cepheid variables has served as our primary standard candle for measuring intergalactic distances. These stars pulse with a regular rhythm, their brightness swelling and fading over days or weeks. In a monumental discovery, astronomer Henrietta Leavitt found that the longer a Cepheid's period, the greater its true, intrinsic luminosity. She unlocked a cosmic meter stick, writing that this relation offered a method for determining stellar distances. By comparing a Cepheid's known intrinsic brightness to its observed, dimmer apparent brightness, astronomers could calculate exactly how far away it was. This was the key that allowed Edwin Hubble to prove the universe was expanding. Yet today, this foundational tool is under intense scrutiny. Different methods of calibrating these stellar yardsticks are yielding conflicting results. The European Space Agency's Gaia mission, which is creating an ultra-precise three-dimensional map of our galaxy, provides distances to nearby Cepheids by measuring their tiny parallax shifts as Earth orbits the Sun. When these Gaia distances are applied, the Cepheid scale seems to shift slightly compared to other calibration methods, like using the subtle eclipses of certain binary stars. This might sound like a minor technical disagreement, but its implications are cosmic. The calibration of Cepheids directly impacts the first rungs of the cosmic distance ladder, which in turn influences our measurement of the Hubble constant, the universe's current expansion rate. This discrepancy feeds directly into the Hubble tension, that troubling conflict between the early universe's predicted expansion and the modern universe's observed faster rate. A key battleground in this calibration war is the Large Magellanic Cloud, a satellite galaxy of the Milky Way. Because it contains many Cepheids and is relatively close, It has long been the cornerstone for setting the 0 point of the period-luminosity relation. But even here, different techniques produce slightly different distances, casting a shadow of uncertainty on what was once considered a fixed reference. This forces a deeply unsettling question. If our most trusted cosmic mile markers have an inherent fuzziness, how can we be certain of the vast distances we have assigned to galaxies, or the ultimate fate we have predicted for the cosmos? The reliability of our entire cosmic map depends on the steady beat of these pulsing stars, and that beat may not be as uniform as we once believed. This fundamental challenge to how we measure space connects to an even deeper mystery about the nature of time itself and a subtle anomaly in the orbits of our oldest planetary companions. Our own Milky Way spins with a hidden rhythm, a secret written in the motion of its stars. If the Sun and planets were the only source of gravity, stars orbiting far from the galactic center should move slower, just as Pluto crawls compared to Mercury. Yet when we measure their speeds, we find a shocking consistency. Stars at the distant edges of the galaxy whirl around just as fast as those closer in. This is the rotation curve anomaly, a universal feature of spiral galaxies that screams one thing: most of the matter is missing. The astronomer Vera Rubin, whose meticulous work provided the most compelling evidence for this, put it simply, saying it became clear that what you see in a spiral galaxy is not what you get. Her observations revealed that galaxies are embedded within vast, massive halos of something invisible, something we now call dark matter. This cosmic phantom provides the extra gravitational glue to hold these fast-moving stars in their orbits, preventing them from being flung into the void. But the plot has thickened with the discovery of galaxies that defy even this explanation. Some ultra-diffuse galaxies, ghostly collections of stars with very little mass, show rotation curves that are almost perfectly explained by their visible matter alone, with little room for dark matter. Others seem to be overflowing with it. This strange inconsistency has forced physicists to consider a radical alternative, that our understanding of gravity itself is incomplete. This idea is known as modified Newtonian dynamics, or MUND. It proposes that gravity behaves differently at the extremely low accelerations found in the outskirts of galaxies. Instead of an invisible halo of dark matter, a subtle change to the laws of physics could make stars move faster without any extra mass. Think of it like this: on Earth, gravity pulls you down with a familiar force. But in the deep emptiness between galaxies, where gravitational pulls are almost immeasurably faint, MUND suggests that gravity gets a slight, unexpected boost. This tweak can remarkably reproduce the flat rotation curves of many galaxies without invoking a single particle of dark matter. For decades, this has been a battle of paradigms: dark matter versus a modified law of gravity. But recent observations are challenging both sides. Some galaxies match MUND predictions perfectly, while others, like those with a puzzling lack of dark matter, are a serious problem for it. At the same time, the dark matter model struggles to explain why these exotic, diffuse galaxies would have such wildly different amounts of the invisible substance. The Milky Way's own rotation curve stands as a testament to this mystery, a smooth, flat line that tells us our home is wrapped in an enormous, unseen embrace. So we are left with a fundamental question for the cosmos. Is the universe filled with a ghostly form of matter that refuses to be seen? Or are we finally seeing the limits of Newton and Einstein's gravity, a law that begins to bend in the profound quiet of deep space? The same rain of cosmic rays that whispers of distant violence also carries a message of a broken limit. Physicists predicted that the universe itself should act as a prison for the most energetic particles. This theoretical barrier is known as the GZK Cutoff, named for Greisen, Zatsepin, and Kuzmin. Their work showed that any proton with an energy beyond a certain staggering threshold should not be able to travel far. It would inevitably smash into a photon from the cosmic microwave background, the leftover glow from the Big Bang. In that colossal collision, the proton would lose most of its energy, creating a shower of new particles. The entire cosmos is filled with this faint radiation, making it an impenetrable wall for the most powerful cosmic bullets from other galaxies. The universe, it seemed, had a built-in speed limit for these projectiles. Yet our detectors keep catching them. Researchers at the Pierre Auger Observatory, a vast array of detectors in Argentina, have confirmed this violation. They note that the flux of these ultra-high energy particles, while small, is real, and it demands an explanation. How are these particles reaching us with energies that should have been stripped away over millions of light years? The Greisen-Zatsepin-Kuzmin mechanism is a cornerstone of our cosmic ray theory, and its violation points to a gap in our understanding of particle propagation through the universe. One possibility is that their sources are surprisingly close by, within our local supercluster of galaxies. Perhaps a nearby active galactic nucleus, with its supermassive black hole spewing jets of plasma, is acting as a hidden particle cannon in our cosmic neighborhood. Other theories are even more exotic, involving the decay of hypothetical structures in spacetime known as topological defects, relics from the universe's phase transitions in its first moments. A stunning example arrived in 2021 with the detection of what was later nicknamed the Amaterasu Particle. This single subatomic projectile, observed by the telescope array in Utah, carried an energy exceeding 200 exa-electron volts. It was the most energetic cosmic ray seen since the Oh My God particle 3 decades prior, and its arrival direction pointed back to a seemingly empty void in space, a region with no obvious galaxies or known accelerators. This only deepens the mystery. What cosmic engines hidden in plain sight are capable of defying a fundamental limit of physics and hurling such unimaginable projectiles across the cosmos? These high-energy particles are not just breaking records, they are challenging our most basic models of how matter and energy move through the vast distances between the stars. Gravity's lens is not just a tool, it is a storyteller, and sometimes it tells a story we do not fully understand. When we gaze at massive galaxy clusters, we see their gravity acting as a natural telescope, warping the fabric of spacetime so dramatically that the light from galaxies behind them is stretched into luminous arcs and strange multiple images. This is gravitational lensing, a direct confirmation of Einstein's predictions. Yet, when astronomers meticulously map this warping to weigh these clusters, they find a persistent anomaly. The lensing effect is far stronger than the pull from all the visible stars and gas can possibly produce. This is one of the most powerful, direct proofs of dark matter's presence, an invisible mass bending light from behind the cosmic curtain. Astronomers studying the now famous Bullet Cluster described it as a cosmic collision that literally separated the stuff we see from the stuff we cannot. In that violent event, the hot gas of normal matter, detectable by its X-ray emissions, slammed together and slowed down, but the dark matter, inferred from the lensing map, sailed right through the collision, leaving the bulk of the mass in a different location than the visible matter. It was a clear, stunning snapshot of dark matter's ghostly nature. We used 2 primary methods to read this cosmic distortion. Weak lensing creates a subtle shearing effect, stretching the shapes of thousands of background galaxies in a coherent way, allowing us to chart the overall mass distribution like a topographical map. Strong lensing, the more dramatic version, creates those brilliant arcs and multiple images of a single galaxy. acting as a precise probe of the very densest regions of the cluster. But the plot twists with clusters like Abel 1689. This colossal assemblage of galaxies is one of the most powerful lenses we know, its gravity painting a spectacular spiderweb of distorted light across the sky. Yet, when models try to reconcile its lensing map with the expected behavior of simple, cold dark matter, tensions arise. The distribution of mass seems slightly off, the peaks of dark matter density not aligning perfectly with the predictions. These subtle inconsistencies have forced physicists to consider more complex possibilities. Perhaps dark matter is not entirely cold and non-interacting. Maybe it has a weak force of its own, a self-interaction that causes dark matter particles to nudge each other, subtly changing how they clump in the heart of these immense clusters. This self-interacting dark matter could smooth out the central densities, potentially solving the anomalies we see. The other contender, of course, is a more radical rewrite of the laws of physics itself. Proponents of modified gravity theories argue that the lensing effects are not caused by invisible matter at all, but by a fundamental misunderstanding of how gravity works in the realm of the extremely massive. They strive to tweak Einstein's equations to make the light bending appear without the need for any dark component. So as you look at these breathtaking images of cosmic arcs and rings, consider the profound puzzle they represent. Is your view of the distant universe being warped by an immense, unseen shadow, or is the force of gravity itself revealing a new layer of complexity on the grandest scales? This cosmic warping of light does more than just reveal mass. It connects to the very geometry of the universe and a number that seems to be changing before our very eyes. These cosmic voids are not merely empty space, they are active, expanding elements in the architecture of the universe. Imagine the cosmos not as a uniform sea, but as a vast foam where galaxies cluster on the dense walls of immense growing bubbles. These bubbles are the cosmic voids, regions of breathtaking emptiness that can span hundreds of millions of light years. The most famous of these is the Boötes void, a spherical chasm so colossal that our entire local group of galaxies would be just a tiny speck within its staggering volume. Astronomer Robert Kirshner, who helped discover it, described it as a giant hole in the universe, a place where you could expect to find thousands of galaxies, but instead find only a few dozen. This profound underdensity challenges our models of how the cosmos clumped together after the Big Bang. The standard picture of structure formation, driven by dark matter, struggles to explain why such a vast region remained so empty. These voids are not static, they are dynamic entities. As the universe expands, the gravitational pull of the surrounding dense walls is weak, so the space within a void expands faster than the cosmic average. This creates a local acceleration, a miniature echo of dark energy's effect on the entire cosmos. We can actually detect the ghostly imprint of these voids on the oldest light we see. As light from the cosmic microwave background travels through an evolving void, it climbs out of a gravitational well that has become shallower during its journey. This subtle loss of energy, a phenomenon called the integrated Sachs-Wolfe effect, leaves a specific, cold fingerprint on the CMB map. Remarkably, when we cross-reference the positions of known supervoids with the CMB, we find these telltale cold spots, a direct observation of the interplay between these empty regions and the primordial radiation. This leads to a profound and reflective question. If the emptiness within these voids expands faster than the rest of the universe, could they be a localized key to understanding the global mystery of dark energy itself? Do these great cosmic nothings, these bubbles of near vacuum, hold the secret to the force that is driving everything apart? Even the emptiest space in the universe is not truly empty. In the eerie quiet between stars, at a scale far smaller than the atom, the void itself is alive with a seething, temporary chaos. This is the quantum vacuum, a state where pairs of virtual particles and their antiparticles constantly flicker into and out of existence, borrowing energy from nothing for a fleeting moment before annihilating each other and vanishing. This ghostly activity is not just a mathematical curiosity. It exerts a real, measurable force on the physical world. The Dutch physicist Hendrik Casimir first predicted this strange phenomenon, stating that his effect demonstrated how two perfectly smooth, neutral metal plates, placed incredibly close together in a vacuum, would be pushed toward each other by the invisible pressure of the quantum foam outside them. His reasoning was elegant. The space between the plates is so narrow that only certain wavelengths of virtual particles can fit, while the vast space outside allows for all wavelengths. This imbalance in the quantum pressure from the outside pushes the plates together with a faint but undeniable force. This Casimir effect has been confirmed in laboratory experiments, proving that what we call nothing is actually a turbulent sea of transient energy. This leads directly back to the cosmological constant problem, the worst prediction in physics. The energy of this quantum vacuum, known as zero-point energy, should be immense, creating a repulsive gravitational effect that would have torn the cosmos apart instantly. Yet our universe expands only gently, meaning the observed vacuum energy is almost zero, a baffling cancellation of 1 part in 10 to the power of 120. The Casimir force is a tiny, local glimpse of the colossal vacuum energy that our theories say should be there, but on a cosmic scale it somehow is not. This paradox strikes at the heart of our quest for a theory of quantum gravity, suggesting that our understanding of spacetime on the smallest scales is fundamentally flawed. Today, engineers building nanoscale machines must account for this ghostly force, as it can cause microscopic components to stick together, a practical nuisance born from the deepest principles of quantum theory. So as we reach the end of our journey through 30 cosmic puzzles, we are left with one final, haunting reflection. If the void itself is not empty, but a vibrant, energetic foundation for all of reality, then what are the true boundaries of physics, and what other wonders remain hidden in the fabric of the nothing that holds everything together? Stephen Hawking once warned that the greatest enemy of knowledge is not ignorance, it is the illusion of knowledge. Our journey through 30 cosmic puzzles is a testament to this profound truth. We have seen how dark energy's repulsive push and dark matter's invisible pull are two sides of a vast unknown, governing 95% of the cosmos. We have encountered quantum entanglements, spooky links, and black holes that threaten to erase information, phenomena where relativity and quantum mechanics wage a silent war. From the lithium missing in ancient stars to the galaxies moving too fast, from the impossible strength of the vacuum to the silent Great Attractor pulling us through the void, each mystery is a crack in the foundation of our current physics. These are not isolated curiosities. They are interconnected symptoms of a deeper reality we have not yet grasped. The same quantum vacuum energy that creates the Casimir effect in a lab contributes to the cosmological constant problem on a cosmic scale. The same inflationary epoch that smoothed the universe may have diluted the magnetic monopoles our grand unified theories demand. This collective challenge is what drives science forward, forcing us to invent radical new ideas. It pushes us toward theories like string theory, which envisions reality as woven from tiny, vibrating strings, or loop quantum gravity, which proposes spacetime itself is composed of discrete, finite loops. To solve these puzzles, we are learning to see the universe in new ways, using multi-messenger astronomy to listen with gravitational wave detectors, while watching with telescopes across the electromagnetic spectrum. Future missions will probe the dark universe with even greater precision, seeking the faintest whispers from the dawn of time. So we are left with a final, transformative question. As these cosmic enigmas slowly yield to our curiosity, how will they fundamentally reshape our understanding of reality itself and our place within its grand, mysterious design? These 30 cosmic puzzles are not isolated curiosities. Each one is a direct challenge to the pillars of modern physics, from the predictable cosmos of general relativity to the probabilistic world of quantum mechanics. Dark energy defies our understanding of gravity on the grandest scale, while quantum entanglement defies locality on the smallest. The missing antimatter and the silent Fermi Paradox question the very conditions for our existence. Every mystery, from the Lithium Problem in ancient stars to the impossible strength of the quantum vacuum, points toward a fundamental incompleteness in our picture of reality. The universe is far stranger, more dynamic, and more mysterious than our everyday experience would ever suggest. It is a living frontier of unsolved wonders, a constant reminder that our knowledge is a tiny island in a vast ocean of the unknown. The legendary Carl Sagan once reflected that somewhere, something incredible is waiting to be known. That incredible something is all around us, hidden in the dark matter halos of galaxies, whispered in the brief flash of a fast radio burst, and encoded in the spooky links between entangled particles. The greatest journey of discovery is not over, it has just begun. To solve these puzzles, we must continue to look up, to question, and to support the scientific exploration that pushes the boundaries of human understanding. If these cosmic riddles have sparked your curiosity, consider subscribing for more deep dives into the mysteries of space. Let us know in the comments which of these 30 phenomena captivates you the most. The next time you gaze at the night sky, remember that you are not just looking at points of light, but at a universe filled with profound questions, each one an invitation to explore